to the negative 1/2, you have factored from this term and that term. Certainly, the second term is now just x squared. Agreed?
Mm-hmm.
So now what's the first term? It has something to do with 1. 4 minus x squared to the 1. Right?
Wait, what?
Like that. See what I'm saying? If you take a negative 1/2 power from a 1/2 power, you're really dividing by that expression, right? When you factor something off, you're really dividing it off, correct? So really, this piece is underneath here as a negative 1/2. So that makes it really a positive 1/2 above, and you combine them together through addition, you get a 1. Okay?
Oh. Wait, say it again?
Yeah. Let's look at it this way. Again, back to the 4x squared plus x. When you factor x from here, right? What do? You subtract its power from this power, right?
Yeah.
And so you get 4x plus 1. You subtract its power from all the other powers. Over here, this is negative 1/2 power. So you subtract that power from this power. So I subtract this number, it adds it. Minus negative 1/2 from that power. So that actually bumps it up to a 1.
Okay.
That's the anomaly of factoring off negative exponents. Okay? Okay, so we got 4 minus x squared plus x squared. 4, right? So we have now 4 times 4 minus x squared to the negative 1/2 equal to 0. All right. Now what? Now I want you to realize that the 4 minus x squared to the negative 1/2 is really on the bottom. Right? This is really 4 over 4 minus x squared to the 1/2. Okay? So therefore, 2 and negative 2 don't even make this 0. 2 and negative 2 are just, again, they're making this undefined. Right? Remember, the negative exponent is really a positive one down below. Right? So there is no place where the derivative is 0. Agreed? There's no place where the derivative is 0.
I have a question.
Yeah.
How did we get to the 4 times 4 minus x squared?
You cancel with x?
Minus x squared plus x squared goes to 0. I just have a 4 sitting here. So I just put it out in front to make it look like the usual case. Like a coefficient 4 times that expression equals 0. So there is no place of import where the derivative is undefined, right? Because those locations make the original function undefined. And there is no place where the derivative equals 0. So therefore, it passes through no horizontal tangents, right? And what else were you saying?
So does that mean there's no critical value?
No critical values. No critical values.
Because
No
you
critical
said
values.
it was
Critical
0,
value,
the
doesn't that mean that there's no change in the function?
negative 2.
Because isn't the critical value pretty much where the function
Since
could
it already
either
doesn't work
change
in the
direction
original
or stay the
function.
same?
it
Not
doesn't
change
have
direction.
to do
Yeah. Not change direction.
So if we set
It's-
this to 0.
what do you mean by
so it would
direction?
be negative 2.
Like it would like critical point it would be like where the function would go from
So
negative
it's
to positive.
there's no
So
You're close. Not where the function goes negative positive. Those are its x-intercepts. Where it goes negative positive. But where it goes increasing, decreasing.
Mm-hmm.
Yes.
So there's no critical
So it
point,
makes it. So
there's
it
no
makes it.
change.
Say again.
But there's no critical point, there's no change.
There's no change from increasing to decreasing.
Okay.
So is there,
Assuming it's continuous, right? You could have some weird undefined location in between here somewhere. There's not one, but there, there could have been one.
The change will impact if you can have a constant line, the x values can change, but as long as the y value is constant, there's not a minimum or a lower minimum, right? Because in x, the y axis determines slope, whether the function type. So if you have a line going through 2.
If you have a horizontal line,
Yeah, if you have a horizontal line going through 2, that would give you a 0 for the derivative, wouldn't it?
it gives you a 0 for the derivative. It's
Because
true.
It's a constant.
It is. It's a constant function, so everything's a local minimum.
And would that be the case in this problem?
No, this is not a constant function.
On that interval.
It's not a constant on the interval. We'll get to it in 1 second. First of all, let's just address what you said very quickly. If you have a constant function, 1, 2. Let's say you have a horizontal line at 2. Okay. So then, does it have any minimums or maximums? That's the question. Any mins or maxes? Yes. Every location on here is a min. Every location is a max. Every location is an absolute max. Every location is an absolute min. Isn't it? According to our definitions, every single dot on that horizontal line is not only a local max and min, but an absolute max and min. Agreed? All right. That's all said.
That's a cheap way out.
It is. You get the definitions, I apply them. That's all it is. Right?
This is all 4.1.
Right? It's 4.1. God help us. So, so now let's get back to no critical values. So what Justin said is correct. This thing should not be changing from increasing to decreasing. You guys know what it means with increase and decrease, right?
Yeah.
Increase, decrease. The function cannot do that now.
Because we said that since
There's no place where the derivative equals 0 or undefined on that interval. There's no place, right? So it's always, this is an important thing to remember, it's always decreasing or always increasing. So now the question is, which one is it? How do you know?
positive.
Because what?
Because there's no way it could be negative.
How do you know? Tell me how you know.
Because of the square root at the bottom.
Because I mean, like, if you start plugging in from negative numbers to positive numbers.
Into what? The function or derivative?
The function.
Oh, the function? No, the function can be negative. Negative 2.
Yeah,
that
but
makes
it's
it-
always increasing.
It's always increasing, but how do you know it's always increasing?
Because if you plug in negative 2, well, since you know it's always going one way, it's never increasing or decreasing. If you plug in a negative number and then a positive number.
Oh, so how did you get from there to there, you're saying?
Yeah.
It must have gone up.
Yeah.
Very good. Okay, that's a logical way of looking at it. The other way to look at it is through the derivative. Your derivative right now was this mess, right? It was this over 4 minus x squared. That was it. That's your derivative simplified. You can make it a little bit better, right? If you move this down, that makes this to the what? This is the first and 3 halves power. So you can kill all that. Okay? So there is your derivative simplified as far as possible. 4 over 4 minus x squared to 3 halves. Can that function ever be negative? No. Because what does the 3 halves power mean? What's that? There's a square root in there, right? The square roots only put out what? Positives, right? We talked about that before, right? As a function, the square root only puts out positives. So no matter what you put in this bottom thing, it's always putting out a positive value, and the top's always positive at 4. So the derivative is always positive. If the derivative is always positive, the derivative is always positive, it means the function is always increasing. It has positive slopes, it must be getting higher. Always.
The x squared also makes it positive.
This x squared?
Yeah, because you put a negative.
It makes the inside always positive, yeah. So any root of even a cube, even if it's a cube of positive, you still get positive. That's true, yeah. Okay, so now there's no critical values. We also know there's no maxes or mins, right? No maxes or mins. Not global, not local, nothing. But not because it's a constant function. All right, let's move on. 4-2.
I'll take a break after this one.
Yeah, we should, because then we have to graph stuff in 4-3. That's where it gets. That's where you're gonna put it all together, right?